second part of FET and its biasing. So up till now we have discussed that our FET, how it will work, region of operation. Right now we are going to discuss. We have understood that the theory of operation of the field effect transistor, uh, we can say junction field effect transistor also. So, as we know that there are two voltages, one that is VGS voltages and VDS voltages. Whenever we apply the VDS voltages, current through the N channel will start flowing. So, as the current will start flowing, the uh, current will be in a particular position, so that we can control by VGS voltages and other types of controlling, that is VGS, that means voltage controlled device. So in a voltage controlled device, what we are going to discuss about the JFET is that the region of operation. So more probably the region of operation can be understood with IV characteristics. So IV characteristic curve is shown over here. As we can say that it is the curve between drain current and the drain source voltage. So in this curve we can understood the relation between these two quantities. So how a VGS voltages will affect to the VDS and the ID current will be going to understand in this session. So first we know that it is the curve between the drain current and drain source voltage, and it can be characterized as, for VGS equals to 0 volt, the drain current is maximum. Why? Because the gate source voltage will be the controlling voltage of the junction field effect transistor, and due to this junction field effect transistor, if we are not providing any kind of control voltage, the electrons will be passing at its maximum level, as there will be no depletion layer will be formed over the regions. So electrons can be passed easily. So that we can say that the ID current, that is drain current, will be at its maximum, and it is denoted as IDSS, that we can say that shorted gate drain current. One important phenomena is shown over here also, that is VGS off. What do we exactly mean by the this VGS off? That is our gate cutoff voltage. That means if we want to operate JFET in the cutoff region, then it should be bring back to the zero voltages. That is our VGS voltages. That is gate to source voltage will be at the zero. The value of VGS that makes the drain current ID approximately equal to 0 is called as cutoff voltage, and it is denoted by VGS of voltages. So first thing, right now what we are discussing is that if we want to operate the JFET in a cutoff region, that means as an open switch condition, then it should be 0. Which quantity? That is our VGS, that is gate to source voltage, which can be also called as the gate cutoff voltage, will be 0, and then JFET will be as an inactive. That means there will be no any kind of voltage flow or current flow towards the channel, as we are keeping the VDS and VGS both at the 0 quantities, and we are not controlling any kind of output voltages during this particular region. So the first region, that is our cutoff region. After that, if we increase the gate to source voltages, drain current ID decreases even though VDS is increased. Now, how it will happen? So we can understand that if you increase the VGS voltages, then there will be start developing a depletion layer over the both the N regions, as we know that the figure suggests some kind of two regions, that is first is N substrate, and there will be two substrates of N P particle, and it will start becoming a thick layer of depletion layer, which we can say that depletion layer will start forming over here, and this depletion layer will cause the current to its lower values. Why? Because the interruption will be over here, as we can see that a kind of depletion layer is being taken place over here, and it will interrupt the flow of electrons, and due to this flow of electrons the output current, that is our ID, will be at its minimum value. So due to this minimum value, we can say that if we increase the VGS voltages, that is our gate to source voltages, drain current ID is also decreasing even though VDS is increased. Now one more important point, that is gate to source voltages reaches a certain value. After that, the drain current will be decreased to 0. If you further increase the gate to source voltages, then a time will occur when the drain current will be decreased to 0. And after that, we can understand that for different VGS, the ID will become constant after the pinch off voltage. In previous session, we have discussed about this pinch off voltage, that is our voltages whenever the flow of current will be completely interrupted by the depletion layers formed over the P regions. And this P regions, what will it do? That whenever this interruption of current will take place at that voltage, we can say that is our pinch off voltage, that is VP, as a kind of pinch is being taken place, or kind of a pinch type figure is forming over here. So it is called as the pinch off voltage, and this will interrupt completely interrupt the flow of electrons. We can also say that the narrow channel pinches off or prevents the drain current to increase any further. That is why the drain current becomes constant for VDS greater than the VP, as we have already discussed in the previous lecture. And the pinch off voltage is the value of VDS at which the drain current reaches its constant saturation value. Any further increase in VDS does not have any effect on the value of drain current. So this is a clear idea about the pinch off voltage and IV characteristics. So IV characteristics is mainly classified in the three regions, that is our ohmic region, saturation region, and the cutoff region. Cutoff region will be what? That at when the transistor JFET will be in the inactive condition. So transistor will be in its inactive condition, that after that then there will be no further flow of current from the channel. So we can understand that One more important characteristics that we need to discuss is that the transfer characteristic curve. Now, what we can understood by this transfer characteristic curve is that in transfer characteristic curve we can show the voltages and the current relationship in the JFET. So, how much current will be at the output side at a particular voltage of gate to source, and how much value of current will be at the output terminals. So, this is called a transfer characteristic curve, and we can say that transfer of input voltage to the output voltage will be taking place at this condition. So, how much the input power is getting transferred towards the output power, we can get a short, clear idea about this JFET. That here we can see that the transfer characteristic curve will be having some IDSS and the output voltages, output current, pardon me. So for the VGS voltages, how much the ID current will flow. So transfer characteristic is the plot of output current ID versus the input controlling quantity, which is gate to source voltage. In this case, for a BJT, the transfer characteristic is a graph of IC versus the IB. As we can say that the BJT is a current controlled device and the JFET is a voltage controlled device. So we are taking VGS voltages on one hand, and on another hand we are taking the ID current. So for a bipolar transistor, the relation between output current IC and input controlling quantity IB is given by, as we can say that IC is equals to beta DC into IB. How it will arrive, then we can show that beta DC is equals to IC divided by IB, and from that value we can clearly state that IC equals to the beta IB. So where beta DC is considered to be a constant, as we know that it is a current gain. So therefore the transfer characteristic of a transistor is straight line, indicating a linear relation between IC and IB. However, the relation between ID and VDS is not linear. The relation between ID and VGS is defined by Shockley's equation, which states that that the ID, that means the drain current, equals to ID is equals to ID is equals to IDSS into 1 minus VGS divided by VP whole square. So here we can say that IDSS is equals to maximum drain current or source saturation current, and VP we know that is our pinch off voltage. The relation between ID and VGS, that is ID and VGS, is defined as a squared relationship which produces a curve which is growing exponentially. As we can say that it is growing exponentially for a point of time. So when VGS equals to 0 volt, ID must be equals to the IDSS, and when VGS equals to VP equals to minus 4, the drain current ID will be 0. So here we can understand this transfer characteristic from this curve. So basically it is showing that how input voltage will vary the output current, and that characteristic curve is called as the transfer characteristic curve. So after this, further we are going to discuss about the pinch of voltage. We have discussed a little bit about that. Now, what do we exactly mean by pinch of voltage? That is, it is the minimum drain source voltage at which the drain current especially becomes constant, and when it will be occur in the IV characteristics. So we can see over here, that is our pinch of voltage. After this condition, the region of operation will be changed. Here we can see that ohmic region is also here. So ohmic region is nothing but the saturation region of BJT, and kind of operation will be provided during this ohmic region. And as we know that the cutoff region is most popularly used for the off condition of the JFET. Here we can see that both the region of operation, and this is the pinch of voltage at which the VGS voltages can control the output current. So this is called as the pinch of voltage. Now, the most important region of operation is that the saturation region, or we can say that the saturation level. How can we achieve the saturation level in the JFET? That we can understand that by that after pinch of voltage, the drain current become constant, and this constant level is known as the saturation level. As we can see that constant values are taking place after the pinch of voltage, and this region of operation will be called as the saturation level. After that, whatever you increase the VDS voltages, that is our drain to source voltage, that will not affect the output current. So that is the saturation region, or we can say that the saturation level will be achieved after that, and this is saturation level will be denoted over here, as we can say that this is the saturation level, and here we can say that there is no any kind of slope is being seen over here in the particular region of operation. So this is called as the saturation region, and this is more oftenly like an active region in BJT. So these are the two basic regions which we have discussed right now. After that, ohmic region, as we have already discussed, that ohmic region is what? That it is a kind of saturation region in the BJT. The region behind the pinch of voltage where the drain current increase rapidly is known as ohmic region. If you will further increase the gate to source voltages, it will not going to affect the uh, particular output current. So this kind of region of operation will be called as the ohmic region. So ohmic region is a particular region of operation for the JFET. So we can say that right now, up till now, we have discussed about the three main regions of JFET, that they are cutoff, saturation and ohmic. Cutoff means what? That in cutoff region, the JFET will be acting as a open switch. In saturation region, the JFET will work as an amplifier, and the third region which we are right now discussing, that is our ohmic region, it will work as a closed switch. And we know that whenever the closed switch kind of region will be there, then there will be no further effect of any changes in the input voltages over the output voltage. So this is the three main operating regions of JFET. One more region, that is our breakdown region. After this values, the JFET will be in the breakdown region, and that region, how can we get that region? That is, when the drain source voltage is high and enough to cause the JFET's resistive channel to break down and pass uncontrolled maximum current, and that value will be considered as the breakdown region. As we can see in the figure, that this is a kind of breakdown. After a certain value or in a certain value increased of VDS, the breakdown region will be available, or we can see the breakdown region at the IV characteristics. So this is called as the breakdown region, and after this particular increase in the VDS, or we can say drain to source voltage, the region will be seen that considerable breakdown can be seen at the JFET terminals. So this is called as the breakdown region, and after that, that is our cutoff region. We have already discussed that the gate source voltage when the drain current becomes zero is called cutoff voltage, which is usually denoted as VGS off voltages. We have already discussed that for the VGS off voltages. So these are the three regions of operations, and we can clearly understand that if you will not provide any kind of input voltages, the ID will automatically becomes at zero value. So this is the cutoff region. Right now we are going to discuss some of advantages of the JFET, and they are, that is, it is simpler to fabricate, smaller in size, it has longer life and higher efficiency, high input impedance, it has negative temperature coefficient of resistance. Here we are concerned about this negative temperature coefficient. I have already discussed in this on this topic in class, that negative temperature coefficient means the if we increase the value of uh, temperature, or we can say that if the temperature of the device will increase, then the resistance will start decreasing, and we can say that more amount of current can be flow through the channel. We can also say that it has high power gain. Some of its disadvantages are that the greater susceptibility to damage in its handling. As we know that negative temperature coefficient is there, so maybe it will be happen that due to the immense amount of increase in temperature, the current will start flowing, as it can cross the particular current handling capability of the particular device, then it will damage the device. And we can say that the JFET has a low voltage gain. Some of its applications are more popular applications. We can say that is voltage controlled resistor, analog switch or gate, act as an amplifier, low noise amplifier, or constant current source. These are the main applications of the JFET. So here we conclude the JFET part, and this is the second part of the junction field effect transistor, which is containing the region of operations and the particular advantages, disadvantages, and applications of the JFET. After this JFET, we are going to discuss about the MOSFET in our next session, and how a MOSFET will work, what are the different types of MOSFET. These are our session outlines for the next lecture. So see ya, and up till goodbye.